record on this computer. All right, let's do screen share now. Okay, sorry about that. Technical difficulties. All right, my name is Vic Kumar, and I'm going to be talking a little bit about functional programming and how we can introduce that into Python. So much like pattern matching, these are new syntactic changes. One second. Yeah, sorry. Okay. So first thing, I'm just going to install a library. It's called PyFX. I'll talk a little bit more about that later. And the first thing we're going to do is we're going to define like what is functional programming. Like we've seen now a lot of these new functional programming languages such as Swift, Elixir, as I mentioned. You have React in the JavaScript space. So what is functional programming? So I've planted the definition right here. Functional programming is based on like a pretty simple premise, and it has like a lot of implications. And the idea of functional programming is that we're going to construct our programming using only pure functions. A pure function is something that has no side effect. And so like, what is a side effect? A side effect could be modifying a variable, modifying some data structure in place, throwing exceptions, reading or writing to a file, drawing to the screen. So any sort of a function has a definition. It returns a value and it takes some sort of input. Any interaction that the function does that does not interact with its inputs or its outputs is considered impure in a functional sense. It's not referentially transparent. A pure function has the property of referential transparency. So that naturally leads to sort of like the next question, which is what is referential transparency? And again, I sort of cut and paste the definition, which is an expression E is referentially transparent. It kind of gives you, if for all programs P, all occurrences E can be replaced, yada, yada. It kind of is like a headache just even to understand that. But fortunately, there's a pretty easy way to prove referential transparency, and that's using substitution. So here we have a real simple program. It's called add numbers. It's going to take a list of numbers, and we're going to set a variable, sum, which is equal to 0. We're going to iterate through that list, and we're going to add all the numbers in that list. So the example is 1, 5, 6, 8. So we're just going to add those numbers, and the result is 20, which seems right. If I add 1 plus 5 plus 6 plus 8, the answer is 20. But on this line right here, you have told me that sum equals 0. So if I think back to like, algebra class or math, if I say that sum equals 0, anywhere that I use sum on the right-hand side of an expression, I should be able to replace it with what it is equal to, and I should get the same result. So in this block of code, instead of saying sum equals sum plus n, I replace sum with its value. You said that sum is equal to 0. So I should be able to replace it, and it should give me the same result that I got in the first function. What do you guys think is going to be the result of this function where I replace sum with what it was supposedly equal to? Anybody? This is an open discussion, and you guys can interrupt anytime if you have any questions. It's like a live coding exercise here.
N.
But what's the answer?
N.
N.
Right.
Well,
a number.
It's a guess. So the answer is 8, because it went to the last value and it did 0 plus 8 and it returned 8. But one thing that we can kind of observe is that 20 is in fact not equal to 8. And so when we said sum equals 0, we know this. This is assignment equals. What we meant to say is that sum is equal to 0 at this point in time, and then later I go ahead and I modify the value of sum, which, as it says right here, is a clear side effect. It violates referential transparency. We can just prove that that's not referentially transparent. And furthermore, like when we really think about this block of code, it looks like sort of innocuous enough, but you've really actually limited your ability to parallelize this code. For example, if I was running this code across 100 processors, there's no way that once this boils down to assembly level language, or it goes to C and then assembly, that you can properly track this shared mutable variable sum across 100 processors. You can't parallelize that operation. And the reason you can't parallelize it when we observe it is because of this shared mutable state that we've introduced with sum. So we're going to do an exercise. Let's say how do I get rid of this mutable state? Can anyone, we can just shout it out. What are some ways that we could think of off the top of our head just to get rid of the state of that function, the variable sum?
Recursion.
Recursion. That is an awesome answer. So clearly recursion is one way. And so we're going to rewrite this function right now. We're going to call it add numbers to. It's going to have the exact same definition here. It takes in a list of integers, takes an int, and then we're going to say return numbers. So we're going to return the first part of the list if the list is, let's just say, a single element. Otherwise, we'll say return number sub 0 plus, and here's going to be the recursive call, numbers 2 of numbers and the remainder of the list, let's say, right? And we'll just test this out. We'll go ahead and copy this block of code right here, and we'll go ahead and do add numbers 2. So here we go. And we got the right answer. We got 20. And there's no state. This is a recursion. So recursion is a way that we can eliminate that state. That's an absolute correct answer. The second way that we might think of is to use a function from itertools. Whoops, what am I doing? From itertools, let's import the reduce statement, right? And so we're going to go ahead and write this. We're going to do add numbers 3. And we're going to go ahead and use another technique. I'll just copy this actually for now and rename it. Okay. So we'll do add numbers 3. And this time we'll say return reduce. And reduce is actually going to take a lambda function of 2 things. And we'll say a plus b. And it's going to work on the list of numbers. So let's test out add. I'll just comment this one out for now. And we'll test out add numbers 3. Okay, so I'm going to add numbers 3. What is the reduce statement in Python? Isn't it from itertools?
Functools.
Oh, thank you. I'm sorry. I'm stupid. Function tools. You're absolutely right. Okay, and that gives us the right answer. Thank you so much for that. So from functools, we introduced reduce, which is a higher order function. So we take in this lambda, and so reduce takes 2 elements of the list, applies this lambda, and it under the hood, it's doing recursion. We can see that we're recursively applying this function to get our result. But those are 2 techniques we can use. We can use recursion, we can use higher order functions, and what we can kind of observe is that these 2 functions satisfy the definition of referential transparency, whereas this one does not. So we're going to get into why this is kind of important, but that's theoretically the concept behind functional programming, that we want our functions to be pure. We want them to obey the laws of pure functions, which is that they are referentially transparent. Does anyone have any questions thus far about that? No? Okay. So we're going to go into like a sort of concrete example. And here we're going to talk about how we deal with emptiness when something does not exist. So to start with, I've created a few classes here, which is a name. A name consists of a last name and a first name. Don't worry about this option part for now. We're going to have a parent. A parent has a name and also a relationship, which is just a string. It could either be mother or father. And then we've created a child. And a child has a mother and a father, both of whom are parents, okay? So with this, let's say that we wanted to write a function that, given a child, gets the first name of the mother, okay? And so we might be tempted to write a function like this, where we get the child, and we're going to use truthiness. If we have the child, and we have a mother for that child, and we have the mother's name, then return the other name. Otherwise, return none. And so I'm going to create a child here, and we're going to test out getting the mother's first name, which should just be mother over here. Oh, yeah, I should probably compile this block of code first. Okay, so I compiled that block of code, and then I'm going to go ahead and run this. And you can say, oh, it's mom. So we could put in any name here. So, for example, if it was like Rebecca, and we ran it, so we can see that this function works. Now, this function has branching logic here. And this branching logic is really to check whether there's a child, whether there's a mother for that child, and whether that mother, in fact, has a name. So you're doing a bunch of branching logic. And I would encourage, like, here there's even a bug. So, for example, it's a subtle bug. What if the name was empty and I ran this code? You can see I didn't actually. Uh-oh. Did it actually run? It should give me none. Let me restart my Jupyter Notebook real quick. Let's see if this works. Sorry about that, guys. Experiencing a little technical difficulties. Okay, I'm back in my notebook. Let me clear the kernel and rerun the cells that I want to. Okay, so we'll start by installing a library. Okay, that one worked. We'll go ahead and run these classes. Okay, so this was the function that we had where we were trying to get the mother's name, and we got mom. But say I used an empty string here, and oh, it did get the empty string. Yeah, I thought it would actually return none. But there's branching logic here. So the functional way of doing this is to use a class called option. So we're doing a lot of this checking for sort of truthiness, if an object exists or not, if it's empty. And we could sort of abstract that behavior away. We don't need to do checks for emptiness or not. We can use a class, and that class is called an option class. So option, if we think of like inheritance, we have a parent class option. An option has two classes, which are subclasses of option, which are called sum or none. And so now instead of using child.mother.name, I'm going to use the wrapper that I wrote, where we just wrapped last name inside of an option. And what we're going to do is we're going to rewrite this statement as get the mother of the child, get the name of that mother, and then get the first name. Otherwise, give me no name as the return value. So let's try the first example with a child that actually has a mother, and the name should be Karen here. And you can see, okay, so that works. So instead of doing like branching logic and checking if something is empty or not empty, what I've done is I've taken my input object of child and I've just applied a series of functions to it. Get me the mother, get me the parent, get me the first name. What we can also kind of see is that this is a more fluent API style. Everything reads from left to right. I take an input value and I read it from left to right, and I apply a series of functions. And that's opposed to like having if statements, nested if statements. So we've improved sort of like arguably the readability of that code. And another thing that we can do, so we're going to go ahead and run the second test where there is no mother of this child. And we're going to try to go ahead. I had it in the other block. Whatever. I was just going to comment this one out and get this one. So this one does not have a mother. So we can see it goes to the or else block, no name. So that's one of the functional types that we get introduced to, which is option. That's how we deal with emptiness in a functional sense. We don't write if statements and stuff like that. If statements are replaced with option, filter, kind of operations that you would see on a map, reduce, those kind of operations read left to right, and they eliminate the need for explicit branching logic. Do I have any questions so far?
Does the chain you've got there with like flat maps, etc., does it short circuit to the get or else? Does it like say, does that basically trigger invocation of the?
Yeah. So if there's no parent, if the parent is like empty, for example, so like if this was empty, it doesn't run the next statement. This doesn't get run. The flat map, I mean, it's not like really a short circuit, but it doesn't get run. It only runs on the success case if there's something in parent get name. Does that answer your question, Aru, or no?
It does. Thanks.
Okay, so we're going to deal with a second case. So we talked a little bit about how emptiness might be handled by using a class. So I imported this at the top. It's called PyFX. So I took like an initial crack at writing some of the functional classes that you might see. Option, try, either. Hold on one sec. Let me mute myself. Okay, thanks guys. So second case, okay. So I wrote this library called PyFX, which introduces some of the classes that you might see in a more functional language, like say Haskell or Scala. The four classes that are covered are try, option, either, and future. So you can actually do asynchronous operations where you chain them left to right using map and flat map, and don't have to worry about some of the side effects that might happen when you do asynchronous programming. But for right now, we're going to talk about dealing with exceptions, because that's another case. If I go up to the top of this, you can see right here, it says that throwing an exception or halting is a side effect. It's exactly like this example that we had here, where it just doesn't follow the laws of referential transparency. It makes the function impure. So anytime you have like a raise except block in Python, you're writing something that is not functionally referentially transparent. And so we saw our classes up here. Where were they? Name, parent, and child. And so I'm going to create two strings. C1 is actually like good. The child, every attribute actually maps. C2, I've made like a deliberate mistake. In the mother object, there's no attribute called first name wrong. Mother doesn't have that. So what we're going to do is kind of go through an example where we try to take this string and serialize it into the objects that we have, because that could raise an exception, like that could raise an error. We can see here that C2 is not correct. Okay, so the first example that we have is our imperative style here, where we're going to do a try and we're going to do a type error, and then we're going to check the attributes in the attribute dictionary. If name exists, load the name. If the mother exists, load a parent object, so forth and so forth. And we're just going to go ahead and first we're going to go ahead and we're going to test this out with the good data, the one that actually works. And so you can see we got Phoebe, because Phoebe was the first name of the good object. But what happens if there's sort of an exception here, right? Oh, okay, here we go. So I got an unexpected argument, first name wrong. And I raised that error, which is impure. So the way that we deal with that in a functional sense is very much like we dealt with option. You never throw an error. You shouldn't throw an error in Java code. You shouldn't throw it. If you're writing functionally, you don't throw an error. You return an error. Every function has a return value, and an exception is actually no different than any other class that we might use. An exception can be returned. And so that object is actually called try. When we looked at option, when we talked about emptiness, we had this parent class called option, and we had two subclasses of option representing some and none. And that represented the behavior of if something was there or if something was empty. Likewise, we have a try class, and there are two subclasses of try called success and failure. So now I don't need to throw an exception. My load name function is going to return an object which could either succeed or fail. And we can see right here how much more explicit that is. That when I look at this function here, if I was just to look at the signature and not even look at the implementation, I don't know that this function could raise an error. Like, you don't actually have any idea. But looking at the function signature here, oh, it returns a try of string. So I have to deal with the failure case. So we're going to go ahead and do the exact same examples that we did of JSON parsing. So first we're going to go ahead and do the good block. And you can see that we got Phoebe. And now we're going to go ahead and take a crack at what happens when we do something that does not work. Okay, so I actually got couldn't deserialize. So I got to this failure case right here. And I also like optionally, I could handle this. Like I could add blocks where I recover and take a look at like what the actual exception is. So like exception, and say like, I think this takes the lambda. Child has no, oh, because it's a child, sorry. I'll scratch that. I won't go into recover for now. But so the blow example is a way of doing the same thing that we did up here, but we're doing it without side effecting. We're checking if there's a failure on the try and simply printing out that, okay, there's an error. But in reality, we're returning none. So that's sort of the breakdown right there, that in functional programming, we have types that abstract away common behaviors that we have, patterns that we have in programming. For example, checking if something is null, if something is none, dealing with exceptions. I didn't cover either or future. That might be like some talk down the line, but that is essentially it. Oh, someone said make the text bigger. Damn, I should have seen that a long time ago.
So are you taking questions right there?
Yeah, I can take questions. Sure.
So obviously functional programming has a very like vibrant and present community. What's kind of the landscape of functional programming libraries and kind of frameworks in Python?
So
Like
sure. So like Python, for example, like list and map comprehensions are considered like very functional because they're actually constructing things in an immutable way. Like when we saw that example about mutable state, that's like something that you just don't want to do in functional programming. Like why? So when you think about it, it's like a constraint. I know I can solve the problem by adding mutations in state, but that makes the code very hard to reason about. That's actually the premise, you know? So when you look at like stuff in func tools, all the map, reduce, that's functional because you're using a lambda, and then list for comprehensions, but they don't have like these are called monadic types. So they don't have the monads that you see in Haskell, like maybe, or option and optional got introduced in Java 8. So those types didn't exist. And that's what I kind of tried to write out in a little, my first try at a library. But great question. Does that help out any? Oh, there's like pi monads and a couple of other things on, like I Googled things that were trying to do it, but those are actually very like category theory heavy. They're not giving you actual classes. They're giving you like the base, like a monoid and a functor. And then you could potentially build these classes from those libraries. But I was like,
about endofunctors, yeah.
Yeah, so a monad is an endofunctor in the category of monoids. That's what it's defined. Yes, that's the technical definition. But what
I was going to say it. All right.
what you should focus on is the behavior of like you're abstracting common behavior. If throwing exceptions, and you're doing it using the same like behavior, map and flat map. They're like your left and right hand. And so you just take an input, you apply a bunch of functions to it, and you get some output. That's how a program should run. You shouldn't have people write try except within try except. They have to catch one exception out of this several exceptions that they've thrown. And that's like, I mean, personally, like I'm just gonna say it, that's hideous. That's like not a good way to write code. And neither is using mutation all over the place. It makes code unreadable. It makes it harder to maintain. And that's the premise. Like, you know, if we could just read our code left to right and make it pure, we wouldn't have bugs in our software that cost so much money, you know? I should stop recording.